Welcome. I want to talk a little bit more about the fusion inequality and also mention 4 mathematical works from the first part of the 20th century, which actually are, important in this context. We have a finite abstract simplicial complex, something which has been introduced in 1907 by Max Dehn and Paul Heegard, and we have Betty numbers attached to each open set and closed set. They are defined algebraically using a great idea of Hodge, who realized there is just an analytic way to get to the cohomology groups just by looking at harmonic spaces of harmonic functions. So this makes everything much more elementary, especially then with an idea of 1944 of Benno Eckmann, influenced by Heinz Hopf. He mentioned Heinz Hopf. Also here in the context of finite topologies, there was Alexandrov. If you look at these old papers or old books of Alexandrov and Hopf, these topology books, this is all finite, essentially kind of influenced by finite ideas. But we look just at combinatorial versions. So we have a finite set of sets. We attach to this object G, we attach a matrix, a finite matrix, and then we look at the kernel. A kernel consists of several parts, and we can compute the dimensions of these kernels and get then the Betty numbers, and that's what Benno Eckmann pointed out in that work. Another great idea, which Atia mentioned, is that Hodge and Dirac were neighbors in Cambridge, and they had neighboring offices, but they never talked to each other, and Atia finds this very fortunate, because if they would have talked and would have put the Dirac operator and the Hodge theory together, they would have already done kind of much of the work which then Atia was able to do. This combination of these two ideas of taking the square root of the Laplacian, which in this case is actually just in the Hodge case is very, very simple, because we have just L is equal to B plus B star square. It's already, we don't have to introduce Pauli matrices or Clifford algebra or Dirac matrices or anything to go. It's already built in, because we are essentially already in the exterior algebra, which is kind of just part of that Clifford story. So it is very, very natural to look at that, and very helpful also to look at that, for example, to have a wave equation. So the Schrödinger equation here is actually produces then waves, relativistic invariance. That's kind of one of the major ideas of Dirac. In the discrete, this is also very concrete. So this is a concrete matrix. 2012, 2013, already I used this, but that was not mentioned in Eckmann's. But maybe one of the things I wanted to say is kind of, I think there is a relatively simple proof of this fusion inequality, which I think about this as a simplicial complex here, and maybe I just cut away an open set. So this is an open set, and then this is a closed set here. Is we can look what happens when we are taking such a situation, and we just move one part here. We take a little bit more of the closed set, and we move it to the open set. So we can look what happens when we do this transition, what happens to the Betty vectors. Now there are 2 possibilities which happen, and maybe I show that kind of just take a random complex, and I just remove points, remove sets from one and move it to the other, and just see what happens with the Betty vectors. So there are 2 things which can happen, and that's kind of the simplest thing. Is what happens is kind of, if you just have, if you have 0-dimensional space, it's just a finite set of points, and then so this is a finite set of points, is both open and closed. It's closed. and you have if you move one to the other, what happens is that here there are some other things which can happen. For example, here when we take this, this is a closed set here. When we take this edge away, then the closed set consists of 2 points, which means it is disconnected. B0 has grown from 1 to 2. That's this possibility here. That can happen in any level. There's a dual part on the open set. What happens when you add something to the open set? You somehow close holes. So this open set here, this triangle, has a Betty vector 0, 0, 1. And what happens when I add a one-dimensional simplex, what happens is this goes away, and actually the Betty vector afterwards is 0. And this can be understood also from a point of view of algebra. What happens, and especially when you look at the Dirac operator, what happens when you remove one element of the simplicity complex, what it means is actually you just cut away one row and one the case row, case column of the Dirac matrix. And then, but if this is kind of verified, that's a thing to verify. If this is verified, and if one can show that this case doesn't happen together with this case, one has even more information. One has information that the changes happen always with adjacent forms. For example, the K form and the K+1 form change together. That's it for today.